Hello scholars, welcome back. Mr. Hinkle here. In this lecture, let's discuss pressure in the ocean, and I could summarize this entire lecture right here. The deeper you go, the higher the pressure. Okay, thank you very much. Goodbye. See you tomorrow. Just kidding. Let's dive in a little bit deeper. Let's discuss the properties of pressure in the ocean and explore the relationship between pressure and depth. Okay, so definition, ocean pressure is the force exerted by the weight of water above a given point in the ocean. All right, why don't we set this up a little bit? Our lecture is on pressure, marine provinces. Here's the continental margin, the deep ocean basin, the mid-ocean ridge, the deep ocean basin, the continental margin, and the ocean surface. Now that we've got our framework for understanding, we can start to look at the relationship between pressure and depth. And this is useful because pressure and depth influence ocean circulation. It changes what the marine species are doing down there, how they adapt to such intense pressure, and then how we are actually operating machinery in the ocean and on the ocean floor. Our units are going to be pascals or atmospheric pressure. So air has mass and therefore has weight. All of the air that is above me right now, I'm in Fresno. We're at around roughly 200 feet above sea level, so pretty much we'll call it sea level. All of the air above me is exerting an influence of pressure. Pressure is related to depth. So let's do this. Here I am. That's me hanging out. And then the weight of all of the air above me we'll consider at sea level to be 1 atmospheric pressure. Now, there's a relationship between pressure and depth in the ocean where every 10 meters you increase by 1 atm. So why don't I do this? Let's do this. I'm going to set this up. So for every 10 meters, you get an increase in 1 atm. But at the surface, you're already at 1. So that means 10 meters deep, what is the pressure? 2. You got it. Go another 10 meters deep to 20. The pressure is 3 to 30. So on and so forth. So here is my favorite metaphor. You, me, our classroom, 30 individuals, let's say 100 of us decide we want to play to make the biggest dog pile ever made. You know, dog pile like when you're a little kid and you jump on your friend and you want to be the person on top because the person on the bottom is getting crushed. We know that intuitively. So there's 100 of us. The person on the bottom feels the weight of all 99 people above that person. The person that's number 50 feels the weight of the 49 people above them. And the person on the very top doesn't feel the weight of anyone. So there's a direct relationship of pressure with depth. Because the deeper you go, the more water is above you. When I'm here, there's this much water above me. When I'm here, now it's this much water. If I'm here, now it's this much water. Pressure and depth are related roughly 1 atm for every 10 meters depth. The deeper you go, the more water is above you. The greater the weight of that water, the greater the pressure. Summarized so succinctly. Okay, factors that are going to affect pressure, well, depth, obviously, with this relationship of increasing depth with pressure, but density will also affect the pressure at various locations. What affects density? Density is impacted by temperature and salinity. So if you're starting to notice that these key topics in physical oceanography do not happen in isolation, that they're all affecting each other and they're part of a greater whole, then that is a great observation. Sound and temperature and pressure, light, all of these physical and chemical, salinity, dissolved gases, the properties of water, all these physical and chemical properties of water interact to provide us a way that the oceans function. Oceanography is an interdisciplinary science. It takes geology and meteorology and physics and chemistry, and it brings them all together in order to understand this beautiful, beautiful environment called the ocean. So, another thing that affects will be geography, where it's located. Now, to think about marine adaptations, which is what I'm setting up here, there's a couple key laws we want to talk about. Boyle's law and Henry's law. So Boyle's law, volume of gas is inversely related to pressure. Basically, if you have air in your lungs, the deeper you go in the water, that air is going to compress. Henry's law says at higher pressures, a fluid will contain more dissolved gases. This is important for dissolved gases in the ocean, chemical oceanography, where some of the dissolved gases are going to be nitrate and nitrite, carbon dioxide, their availability, their abundance that happens in harmony with oceanic circulation to provide nutrients for primary productivity. Okay, we got way out of physical oceanography, but it's a property of the pressure, and here's those webs that are spinning and weaving all back and forth. A property of the pressure that says the higher the pressure, the more dissolved gases that are down there, the more nutrients that become available through oceanic circulation to photosynthetic algae, phytoplankton, that form the basis of the food web. What the heck? From pressure to primary productivity? That's awesome. I love what just happened here. So let's take it to the deepest place in the ocean. For example, the Mariana Trench has a length. It's here, which is an oceanic crust and oceanic crust subduction zone forming a deep ocean trench, the Mariana Trench. The depth is about 10,984 meters, or around 11K, 36,037 feet, super deep. The pressure down there is 1.1 thousand bars of pressure, 8 tons per square inch, or 15,750 psi. I pump up my bicycle tires to around 50 psi. If you're a road biker, you might pump up your bike tires to 100 psi. Your car, let's see, I pump my car tires up to about 30 psi. So 15,750, that's a lot. That's a lot of pressure. Marine organisms have to adapt to these extreme pressures. They do things like, well, for whales, they have collapsible lungs, flexible rib cages, efficient respiratory systems, which basically means that they turn off parts of their body that they don't need to function while they're diving deep, and they don't breathe compressed gases. The deepest diving whale ever recorded, because I mean there could be some deeper divers out there, but we don't know, is the Cuvier's beaked whale. Dove to a depth of about 3,000 meters or 9,800 feet for 222 minutes. That is amazing. 3,000 meters. That's going to be roughly 300 times the amount of pressure at the surface. Wow. For a mammal like you and me. Really amazing. So, summarizing, there's a lot of adaptations to marine life, and we'll get there when we discuss animals of the pelagic environment and animals of the benthic environment. That was just for example to show that there are impacts of pressure on marine life. But really, the take home is The deeper you go in the ocean, the higher the pressure. The higher the pressure, the more you have adaptations for marine life, dissolved gases, which is also going to affect marine life, and impacts on various factors of physical oceanography. It's all connected. They're all working together. We're studying them in isolation so we can understand, but this is a complex system of interactions that make our marine environment. So thank you so much. I'll see you again.